Good morning, everyone. Welcome to our 11th short online conference. This talk is centered around the theme of signal processing, and we are happy to have two speakers today who will give a joint presentation on how can signal processing enhance opportunistic precipitation sensing. Our speakers today are well-known faces within the OpenSense action, Professor Hagit and Dr. Jonatan Ostrometzky, both from the School of Electrical Engineering and Computer Engineering at Tel Aviv University. An electrical engineer by training, Professor Hagit Messer is a leading expert in signal processing and telecommunication, and is one of the pioneers of the current opportunistic sensing era. Aside from many leading positions at different universities, she also helped found the company Climacell, now Tomorrow.io, and is currently also leading the Cellular Environmental Monitoring Lab at Tel Aviv University, together with our second speaker, Dr. Jonatan Ostrometzky. Jonatan also has a background in electrical engineering. He is an expert in opportunistic integrated sensing and communication of the environment, and his research interests also include resilience of wireless networks and power grids. He is currently a senior researcher at the university, where he is also actively involved in teaching and innovative learning. So we look forward to being taught something more on signal processing for opportunistic sensing in this short online conference. The floor is yours.
Thank you very much. I'll share the screen. So, as Natalia presented us, thank you very much, Natalia. Today, myself, Jonatan Ostrometzky, and Hagit Messer from the School of Electrical and Computer Engineering at Tel Aviv University, we will show you a little bit how signal processing can help in our application of opportunistic precipitation sensing. So, for starter, just a quick reminder of what we do here. Probably we all know this by now, but just to make sure, we first start with local rain estimation. This is the standard thing that we do. We're transforming measurements from a CML, commercial microwave link, into a virtual rain gauge, usually located in its middle. So we have the microwave link here. It's a line of sight with a given path. From the properties of the microwave link, frequencies and polarization and length, of course, we have the power law. We assume that the power law can be approximated by this equation here, and it gives us a relationship between the rain and the attenuation. To extract the rain from the attenuation, there are basically two parallel approaches. The first approach is a model-driven one. We calibrate the model parameters, we do a wet-dry classification or extract the rain-induced or the reference level, which is attenuation not caused by rain, take the attenuation caused by rain, and then use the power law. On the other hand, we have the data-driven approaches, which are more modern in recent years. There's a lot of studies that used data-driven, which is a machine learning or AI approaches. Generally, we take the labeled data, which is results or labels from rain gauges usually, and take the attenuation data and try to find a machine learning algorithm or machine learning network that can make this relationship in an optimal manner. And there's plenty of works. Hi, Christian, there's many others. So this is our playground for today. And the talk today, we will show you, hopefully, how can signal processing help us. We present and answer three questions. The first and the last one, Hagit will present in a minute, and I will present the second one. We first start how much performance is lost when we reconstruct the rain field. while we are treating the CMLs as a single virtual rain gauge in its middle. Maybe there's other ways to do it which are better, maybe they're not, we will see in a few minutes. Then I will present how much rain information we actually have or can we extract from minimum and maximum samples. Not instantaneous one, but many times we get the minimum and the maximum values within a given 15 minutes, for instance. How much information about the rain do I have from those min-max samples compared to instantaneous ones? And the last question, Hagit will present, how is the commercial microwave link network topology, their deployment, related to the resolution and accuracy, or then how well can you reconstruct the rain field from a given deployment? What is the relation between the deployment, the location of this microwave links, and the rain map? And so with that, I will now give the stage to Hagit for the first question.
Okay, thank you, Yoni. Thank you, Natalia. Thank you for being here. Actually, these three items are examples of the approach that we use in signal processing, and we can see how it helps our application field, which is by nature interdisciplinary. And the first question that Yoni already showed you is regarding the application of rain mapping. Can you move to the next slide, Yoni? And I believe you are all familiar with it. We have a given network of CMLs, like you see here on the left. In Israel, for example, we have links measurements from different cellular providers in different colors. Each link, which is presented here, actually supply us with a time series, as you can see here in number 2, which is the signal level as a function of time. And you see, indeed, there is a significant attenuation in a rainy period. So this is the basic that Yoni just referred to in the previous slides. And since we have so many sensors, so many links, we can create from all of them two-dimensional rain maps. And here on the right, you see two-dimensional rain maps created from such a data using different algorithms. And actually what we did by this application, we converted a network of commercial microwave links into a virtual weather radar. The most impressive work was published 12 years ago by our colleagues from the Netherlands. And you see here on the left a comparison between a dynamic rain map created by radar and by a commercial microwave links. Definitely you see the similarities, but also there are some differences which reflect some differences in accuracy, etc. Next, please. So this application is widely used now by groups all over the world. Actually, in 2018, almost 7 years ago, Christian presented this poster in a conference in Seoul. It was just before COVID. And you see that groups all over the world, in Europe, in Africa, in South America, created rain maps from commercial microwave links, and most of them use the same algorithms. And I will refer to this algorithm in the next slides. The most common algorithms, and as I said, there are several algorithms, but the most commonly used, and actually in the previous poster, I think all of them were creating using this specific algorithm, is first extracting rain-rate information from each of the links, either by model-driven algorithms or data-driven algorithms, as Yoni explained in the first slide. But the idea is to use the power law that you see here, which relates attenuation with rain rates. And if you don't remember, the three coefficients A, B, and L. L is the distance between transmitter and receiver, and A and B are two coefficients which are dependent on the frequency, the polarization of the link, and also some climatological characteristic like the drop size distribution. Anyway, from these equations, once you isolated the rain-induced attenuation A after pre-processing, you can extract a quantity which you called R, or R hat, okay? And once you extract R hat, the question is what you do with it. And most commonly, in rain mapping algorithms, people assume that this R hat is rough estimation of the rain rate in the middle of the commercial microwave link, like a point measurements, a virtual rain gauge. Of course, it is noisy and so on, but still it's a good approximation. And then they apply standard spatial interpolation techniques like the kriging or the inverse distance weighting. Out of all these points on the map, they construct a two-dimensional rain map. Of course, this approach neglects the spatial spread of the commercial microwave links. Each one of them has a specific length and orientation, but if you converge all the rain rate information into one point, you neglect the spatial spread. And the question that we want to refer to is how much does one lose by ignoring the spatial information? Is it really necessary to use more complex algorithms that employ the spatial information, or is it good enough to assume a virtual rain gauge in the middle of the link? So there are generally two approaches to this question, and here I want to emphasize the difference between the standard approach which are used by people from hydrology or meteorology and from us that come from signal processing. From the environmental science approach, usually it is based on empirical comparison with real data. That's the way they evaluate the performance. And just one example of such a paper, there are several. This paper is entitled Quantitative Analysis of the Performance of Spatial Interpolation Methods in Rainfall Estimation Using Commercial Microwave Links. This paper, which is, we call it semi-real or semi-empirical, it's actually started with radar rain maps from a given area, and then assume that the radar rain maps are the ground truth. And then if this is the ground truth, it applied different algorithms to create different kind of maps, either assuming a single virtual rain gauge in the middle of the link, or more sophisticated algorithms, and then compare their performance. And this is indeed a paper that gives you some idea, but the problem with this approach that the results are usually dependent on the algorithms that were chosen, the specific parameters of the algorithms, and the scenario where it was taken, which climatological environment, etc., etc. And the results are often represented as kind of a scatter plot, as you see here on the right, which compares the evaluated rain maps with some reference. But the reference is never the ground truth, because unfortunately with rain, we don't have the ground truth. We can have it by simulations, but not real ground truth. So what is the signal processing approach? The signal processing approach, can you move, Yoni? Yoni, thank you. The signal processing approach is different. We do some kind of theoretical analysis based on statistical model. And I will elaborate with few words about a parameter estimation approach. In general, the parameter estimation approach assumes that we have a random vector of measurements. It is here denoted by X. And we assume that we know the probability density function of this measurement vector X, giving some parameter vector theta. Okay? So theta is the vector of parameters which are unknown, and these are the parameters that we want to estimate. In our case, X would be the attenuation measurements from the commercial microwave links, and theta would be some measurements of the rain okay, either in each pixel or with different model. How do we estimate theta? We apply some function, which is the estimation procedure on the measurement. So theta hat, the estimate is a function g of x, and I said nothing about the function g. It can be different algorithms that apply on the measurements. So g is the estimation algorithms, and then we have a resulting error, which is epsilon theta minus theta hat, okay? So our analysis is based on something which is referred to as the Kramer-Rao bound inequality. The Kramer-Rao bound inequality said that the covariance of the error, covariance of epsilon, which was defined here as the estimation error, is bounded by a quantity, which I denoted here by phi inverse. Phi inverse is the Kramer-Rao bound. Phi is the Fisher information matrix. And the phi inverse or the Kramer-Rao bound is the lowest estimation error that you can get independent of the estimation algorithm. And the Fisher information matrix can be evaluated directly from the assumed probability density function from the PDF. And here is the equation. And the idea is that once you know or assume some statistical model, you can derive the Kramer-Rao bound, which indicates on the best possible performance, the optimal performance, independent on the algorithm use. So you can actually refer to the optimal performance, and then you can compare any algorithms to the theoretical optimal to see how well you do with this estimation procedure. For our specific problem, if we want to apply the Kramer-Rao bound theory to our rainfall estimation problem, first we need a parametric model for the rain field. And actually, if we look at the literature, there are two commonly used parametric models to model a rain field. One is what you see on the left, to see that a rain cell is kind of a Gaussian shape, which has a maximum in the middle, and then it has some decaying nature. And if you model a rain cell with a Gaussian shape, then the parameter vector theta is what you see here. It consists of the maximal rain in the middle, R0, its location, its width, etc., etc. The other way, and then if you want to make it more complex, you can assume several such rain cells on a given area. The other alternative is to model a rain field by a B-spline, meaning the equation is here. The rain field is a superposition of patches which are B-spline with coefficient Pij. So the parameter vector is the vector theta of all the coefficient Pij. And you can play with the complexity of the rain field by the order of the B-spline. Either approaches will provide you with a parameter vector, and then you can apply the Kramer-Rao bound that I described before, and then you can come up with some results as I show in the next slide. So this is just one example, and we did a lot, as I will show you in the following, to be able to say how much do you lose if you model each link by a single point. We compared the achievable performance as described by the Kramer-Rao bound if we had sensors which are either line sensor, meaning CMLs, with a certain length and orientation, or alternatively, in each location we had only a point sensor, which is like a rain gauge. And what you see on the left curve is the optimal mean square error, spatial mean square error of the rainfall estimation of the rain map estimation as evaluated by the Kramer-Rao bound under some simplified statistical model. So you see the mean square error as a function of the size of the cell. Okay? So what we see here, and this is quite intuitive, if the rain cell is very small, then the links significantly outperforms. If you consider the length of the link, then you can do much better than if you only consider it as a point sampling, okay, which is the orange one. Indeed, if the size of the rain cell is larger, then you can assume as it getting larger, then the rain is almost constant along the link, then you can approximate it by a single point. But you lose it, of course, if the rain is more spotty. So the idea is that you do much better if you have a sparse network, then you should go to better algorithms, more complex. But if you have a dense network, then you can do well by only taking the midpoint of the link as a virtual rain gauge. With the B-spline approach, we got similar results, but I don't have time to go into details. So let's move to some references, and this presentation will be shared with you. Here is a list of references from our group that study this problem using different approaches. And the approaches that we used are either theoretically, as we do in signal processing with the Kramer-Rao bound. We did some simulation studies because if you don't have the ground truth, in many cases you go by simulation. And we did some experimental studies or semi-experimental, as I showed you with the one that we did with the weather maps. So this is my first part, and let's move to Yoni. And indeed, if you have any question, you can either raise your hand or keep them to the end or put it in the chat and we'll get back to you.
Thank you very much. So now I will present and hopefully answer the second question. And the second question that we will show today is how much rain rate information can be extracted from min-max signal level samples. So just a quick reminder, we saw this equation already 4 times today, but the general parallel assumes that our measurements are instantaneous. And this is also sometimes the case. We have a specific sample in a given time index t, which is instantaneous, and we can refer from it to the specific rain rate at that time in millimeter per hour. And indeed, in a lot of cases, this is what we get. And this is the time series of the received signal level. In this case, this is from Gothenburg, from Ericsson in Sweden. In summer 2015, the transmitted signal level remained constant. So the received signal level is actually the attenuation as a function of the time. The sampling interval here is 10 seconds, which is standard for the Ericsson system. Every 10 seconds, we receive an RSL, received signal level power sample. If we analyze it, do some pre-processing and take the attenuation, which is due to rain, put in the parallel, we get the rain in millimeter per hour that the link detected in this specific time index. Usually, we get it in either every 10 seconds, every minute, every 5 minutes, every 15 minutes, etc. It depends on the system, depends on the provider, but this is instantaneous samples. And each sample is actually independent on the other. Of course, there are the dependency of the physical phenomena, but each sample samples specifically what right now happened in the medium, in the air. On the other hand, a lot of systems do not use the instantaneous samples because, again, especially if we take the network management systems, the NMS systems, they don't really care what is exactly happening right now in the microwave link. They just need to know that the link is operational. So instead of reporting the instantaneous samples, we get a minimum sample and a maximum sample within a given time period. Right now, the general consensus in all the companies is 15 minutes. So if we take Ericsson, for example, The system itself, inside the link, indeed samples every 10 seconds the link. But every 90 of those samples, which is 90 times 10 seconds, is 15 minutes. Every 15 minutes, every block of 15 minutes, we only get reported the minimum value and the maximum value detected. That's all. And we have those two samples. Question is, what information those two samples hold? So the challenge is, how can we compare those minimum and maximum samples with the instantaneous ones? Now, when you think about it intuitively, you can think, okay, you have two samples, so it's equivalent to taking two samples somewhere in those 15 minutes. But that's incorrect, because think about it. Right now, we are 19 people here on the Zoom call. If I just say that a specific person, Natalia, for instance, you are, I don't know, 170 centimeters tall. Okay, I only know that you are 170 centimeters tall, just an example. I don't know anything else about all the other 18 people. But if I say that the tallest person here in this call is 195 centimeters, it's still one sample, but I already know something about all the other. I know that there's a person here which is 195 centimeters, but I also know that no other person is more than 195. So I have some information about the other samples, even though I do not have them. So we can use this now new intuition, develop it theoretically, which we did, and we find out exactly how much information can we extract from those min-max samples. So to do this, we first need to have some basic assumptions about the rain. We assume that the rain is a stochastic process, meaning it's random. Every time index, the amount of rain is random. But we need to have very broad assumptions which are logical. The first assumption is the rain, we don't really care which probability or probability function, density function the rain have. There's a lot of literature about it. Some say it's exponential or the gamma distribution or log normal. It doesn't really matter for us because all of those hold to the assumption that we need. The assumptions are, first, the minimum value of the rain is bounded by 0, meaning that the rain is always positive, which is the case. We don't have negative rain, right? And the second assumption is that as we go to extreme rain and rainfall or rain intensities, the probability of it happening is bounded, the tail is bounded by an exponential function. And it is the case indeed, no matter which function of the probability of the rain you take from the literature, well, normal, gamma, exponential, all of them do hold to this assumption. Now, based on these two assumptions, we can go to the statistic of extreme values. Extreme value theory is a branch in signal processing that tries to see what we can do when we have extreme values from some probability, from some event. And K is the number of samples from which I take the minimum and the maximum. In our case, K equals to 90, because we have 90 measurements in 15 minutes. We only get one minimum and one maximum. And we can prove it. We can show that as K go to infinite, but in real world, when K is more than 10, it's sufficient, and we have K 90. The minimum doesn't really give us that much information. Actually, the minimum is more or less converges to 0, but the maximum converges to a specific probability density function, a known probability density function, which is called the GEV, Generalized Extreme Value Probability Density Function Type 1. It's also sometimes called as the Gumbel distribution. And this distribution is known. We can extract the parameter, the theta, from it. And once we know the theta, we know how to go back to the rain parameters, like the average rain or something like that. So if we go back to what Hagit presented a few minutes ago about the Fisher information matrix, which is inverse of the Cronero bound, we can see that in the minimum, the information, this is just a normalization factors, the minimum sample has information more or less like a single sample. But the maximum sample has more and more information as k increases. When we have more samples from which we take the maximum value, I have information compared to more single instantaneous samples. And it goes like log, natural log by the power of 2. The mixture of those, if I have both the minimum and the maximum, is more or less like the maximum, because this goes larger as k increases. So what it means for us, this table, I think, is more or less the main story. K is the number of instantaneous samples that I have within a given block. Let's say 5, 10, 25, 50, 100, 1000. If I have access to all the samples, the instantaneous ones, so the optimal estimation that I can do, if I have an optimal tool, will have information comparable to 5 or 10 or 25 samples, which is the number of samples that I have, the instantaneous samples that I have. If from those samples I only have the minimum, I have information equivalent to one sample. But if from those I have the maximum sample, then it gets interesting, because then I get information which is much more than just another sample. For our specific case, I remind us, we have 90 samples in a 15 minutes interval from which I get the maximum and the minimum. So 100 is close enough to 90. So we can look at this line here. We have about 20 information of about 20 instantaneous samples only in the maximum, which is interesting. I have only one sample, the maximum, okay, and the minimum, but the minimum adds just one. But I have one sample, the maximum value, and it holds information, if I use it correctly, more or less as if I had 20 samples in this 15 minutes interval, which is about a sample every minute, which is interesting, right? So to conclude so far, the maximum attenuation holds more information first from the minimum, okay, but also the maximum and the minimum combined can get us up to 20 instantaneous samples taken within those 15 minutes regarding the information of the average drain in these 15 minutes. Let's conclude this part with some examples. So this is the demonstration. This is a part of the OpenMRG, the open dataset from Sweden. I took a microwave link, which is closest to a rain gauge. This is maybe 100 meters or something like that. And I applied an algorithm using the maximum and the minimum values. Now I just remind everyone, the power law, as I said, is based on instantaneous samples. Once we go to minimum and maximum samples, we need to calibrate the power law. There are a few approaches. This is an approach that I use. I developed it back in the days. I calibrate the parameters of the power law to work with minimum and maximum, and then I get the average drain. There's a lot of others out over in with Remco Ulinet. In 2011, they developed probably you'll know the two-thirds. You take third of the maximum plus two-thirds of the minimum, like a weighted average, and then you get also parallel equivalent to use min-max. This is an example of a time series. The blue one is the rain gauge here, this one. The orange one is the CML, and you can see that both the correlation and the cumulative rain is very good. It also works a different day when we have a lot of dry periods, so it doesn't really matter if it's dry or wet. You can use the minimum and maximum samples just as you use the instantaneous one and get good results, even better depending on the, again, time interval of the samples. If you do it more rigorously, so now I took 8 CMLs, each CML closest to the rain gauge, 16 different rain estimates, and here we can see a scatter plot. In the x-axis is the cumulative rain depth of the specific event. In the y-axis is the correlation coefficient, and in the green pluses, you can see what is the accuracy of those time series. This is an example of time series. What the accuracy of this time series is if I took a single instantaneous samples every 15 minutes. If I have only one sample in 15 minutes, this is the accuracy that I get. If I took the full data set every 10 seconds and use it to calculate the rain, I will get the red triangles here, which is higher. But the interesting thing is that if I use the minimum, maximum, and the calibrated parallel for me using minimum and max, I get something which is much closer to the full data set than for a single sample, which this is a demonstration of the theory that we just presented. So the takeaway message from this part is that the min-max samples at 15 minutes interval, although there are just 2 samples, hold significantly more information than 2 instantaneous samples and can potentially outperform instantaneous samples at higher sampling rate, if once every 10 minutes, once every 5 minutes, etc. Still, min-max probably is the better choice. This is some references, and of course, you will get the presentation so you can go over them later with ease. And thank you. And now I give the stage back to Hagit for the third part.
Thank you, Yoni. Again, as I said, we give examples of how statistical models can help us in getting some general conclusions about the inherent limitations in our problem, the use of CML from opportunistic precipitation monitoring. And please move to the next slide, Yoni. The question that I want to refer now is the following. We have a given topology of CML network, like what we have here in green on the right. So the distribution of the links, the length, the orientation is random. And then we want to create out of these measurements from all these CMLs some two-dimensional rain map, as you see up here. And as I mentioned before, it is doable, it is done, but in many groups all around the world right now. But the question is, how do you set the resolution of the rain map? How do you decide about the size of the pixel? Of course, you can take the pixel, not yet.
Sorry.
You can take the pixels to be large, but you want to have the best resolution that possible. But if you take the pixel to be too small, you may lose some rain events in places where you don't have coverage from the links. So if you want to refer to the resolution question, the answer depends on the rainfall characteristics and the number and the topology of the links. And the way we approach this problem, now you can move to the next slide, is to base our analysis on a theory which was set a few years ago by Dono and Tanner. And it is related to a well-known problem. You see, you may have equation set y equal ax, meaning that you have y. Y is the number the number of equation n. A lowercase n is the number of equation y, and then you have a matrix A, and x of dimension n is the number of unknown. So my grandchildren already know that if you have more equations than more unknowns than equations, the problem is unsolvable. But Dono and Tanner proved that this is not always true, and they refer to a specific case where A is a random matrix and X is a sparse vector. By sparse, they mean that K out of the entries, the n entries of the vector X, are non-zero, and they are put in random location. So it's not full vector, it has many zeros or some zeros at random location. Then they have proved the theory that says that you have what they call a phase transition diagram, meaning that if the ratio between n lowercase and uppercase n, which says this is the ratio between known and unknown number of equation and number of unknown, and also the ratio of the sparsity to the length of the vector x, which is delta, then in this area the problem is statistically solved. In this area it is unsolved. So what we did, and we jump next, Yoni, to the next slides, we actually did it in our problem, where in our case y is the number of the links in the network. A is the translation from attenuation, which is in the vector Y, and the rain measurements in each pixel, which is in the vector X. So indeed, the vector X is larger than the vector Y. And then we want to ask under which condition this problem is solvable in our problem. And what we did it, and we use A of course is the network and it is random. We use the statistical properties of a CML network, which has been studied in another paper. And then you can move to the next slide. We empirically studied this problem, and we have shown that indeed, even to our problem, you have a kind of a phase diagram, meaning that in our problem, the resolution that you pick should be such, the resolution determines, the number of pixels. The resolution that you can pick is such that if you happen to be in the orange area, then the problem is solvable. But if you happen to be in the yellow, in the blue area, then in this case, you may miss some of the spatial information of the rain. And just to demonstrate how this result can be used, let's look at the following example. Assume that you have n equal 200 links, okay? And assume they are uniformly distributed at the area of, say, 15 over 15 kilometers. And now let's say we want to create a rain maps with a resolution of each pixel should be half a kilometer over half a kilometer. Sorry. Meaning that in the area of 15 over 15 kilometers, we have 900 pixels. Then the question is it feasible? Can we have such a good resolution? And it depends on the sparsity of the rain field, and we need the sparsity to be such that we will be around here. If you go to the next slides, we study empirically the sparsity of rain field from radar plots over Gothenburg, over Sweden. And experimentally, we have shown that the sparsity of such a typical rain field is between 0.1 and 0.3, meaning that indeed, with this kind of rain maps, you can use CMLs and get a resolution of half a kilometer over half a kilometer. And indeed, if the conditions are such that you get into the phase diagram, you can even have better resolution. But in general, we gave tools to be able to set the resolution of your rain mapping from CMLs. So that's about what we wanted to show you in this short talk. And just to jump into the conclusion before we open to some question is that what we wanted to demonstrate in this talk, that signal processing is a powerful tool which enables theoretical study of inherent limitation and algorithms design consideration in practical application under statistical modeling. So indeed, instead of dealing with real data, we deal with statistical modeling, and from this statistical modeling, we can come up with general conclusion. So people may ask, how do you know that the statistical modeling is correct? Indeed, we don't know. There are some work about the statistical models of rain, etc., and Yoni mentioned few of them. But fortunately, even if you assume some rough assumption about the statistical modeling, you get results which happen to be robust. So it's not so accurate, but it gives you an idea about, like the example that I gave between the performance of rain gauges and links, etc., etc. So you don't really need to do things with real data, but you can get a general idea about performance, about limitation, etc., etc. For example, in a paper we presented like last month in Edinburgh, one of our students studied the question: if you have a given network of CMLs and you can place rain gauges in the same area, which one is the best place to put the extra sensors? And the answer to such question can be given by signal processing tools like the Kramer-Aubaum. So this is about it, and we are most welcome to have any question or any ideas how to use our tool further. Thank you very much.
Thank you very much.
Thank you, Yoni. Thank you, Hagit, for this amazing presentation. I think it showed us how powerful is the signal processing. And I ask the audience if there are any questions.
Just to mention our webpage of our group, you can find there everything, all the papers, the presentation, information, students. So you are most welcome to visit our webpage. And I see that there is at least one question, so Natalia, go ahead.
Yes, George, you can ask the question. We cannot hear you. Now you are mute. We still cannot. Okay. So you will write in the chat. Are there any other questions in between or comments to Yoni and Hagit?
If you have questions also later, just feel free to mail us and we will answer. Okay, so George should ask, should we always ask for min-max information on signal sampling, whatever resolution? So it's a good question. And again, it depends on what is the alternative. So as we've seen, the min-max has more information than one sample every 15 minutes, then two samples. It has information roughly in the real world, when we checked it, more or less about like 10, 20 samples in these 15 minutes. So if you are presented with an option to get the minimum maximum, or for instance, samples every 5 minutes, I will probably get the min-max. If you given the option to take the min-max or samples every minute, then I will probably take the every minute. It depends on the resolution, but definitely there's some line. I think about once every 5 minutes that the min-max is better than the instantaneous one, yes. Did I answer your question?
Thank you, Yoni. I suppose it was a perfect answer.
Mm-hmm. Thank you.
Yes. So if we do not have other questions now, it will be my pleasure to invite you already to the next conference, which will be in 2 months at the end of September. And the information of the speakers will be given later on our webpage. So stay tuned, and I wish you the nice holiday time. Thank you once again to our speakers today and all of you for joining this morning session, and see you next time.
Thank you very much.
Thank you, Natalia. Bye-bye.
Bye.
Bye-bye.
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 Bye.